We're going to start talking about various types of reactions, and specifically we're going to start dealing with solution chemistry. So this presentation is the basics about solution, just in terms of terminology and how we represent them in chemical equations. We'll get into other aspects later on in the week. So what are our lesson objectives? We're going to define what a solution is, what a solute is, and what a solvent is. We'll identify solute and solvent in examples of solutions. We'll define solvation, dissociate, and dissolve. All of those are slightly different concepts which apply to this stuff. And then we will write ionic equations and write net ionic equations. So to start out, a solute is a chemical in lesser quantity in a solution. A solvent is a chemical in greater quantity, which, if it's not specified, it's water. And the solution usually takes the phase of the solvent, whether that be solid, liquid, or gas. And finally, a solution is a mixture in which the solute is evenly distributed with the solvent, so it's a homogeneous mixture. A solution can be a solid, liquid, or gas solution, but aqueous solution always refers to water with the solute dissolved in it, and we give it by the designation AQ in a balanced chemical equation. All right, so let's see if we can identify the solute and solvent. And I've given you an example of three things that you've probably encountered in everyday life: hot cocoa, brass, and air. And these are all three different phases: liquid, solid, and gas. And I want you to try to identify the solute and the solvent for each of them. When you think you know, go on to the next slide. All right, so hot cocoa. You have probably made hot cocoa from a packet at some point in your life, so that's the scenario we're going to talk about. That hot cocoa powder is the solute, and the water is the solvent. Now in brass, I've said it's an alloy, so it's a mixture of copper and zinc. And we have 70% copper, so that makes it the solvent, and 30% zinc, which makes it the solute. And finally, we have air, which is a mixture of gases. The one that's in overwhelming majority is nitrogen. So nitrogen is the solvent, and everything else is the solute, as far as we're concerned in chemistry. Now, I said I was also going to discuss solvation, so here we go. When you mix something into a solvent, there is an energy associated with that mixing called the heat of solvation, or the enthalpy of solvation. You must break apart the molecules of the solute and mix them into the solvent. The difference in energy before and after mixing is the heat of solvation. Here is a molecular view of the dissolving process for a solid and a liquid. You can see that we have a solid block of stuff, and it gets split into atoms/molecules. We don't really know from this picture. The atoms/molecules of the solute become surrounded by solvent molecules. In particular, this is a picture of water, so we've got water molecules. You can see that the water forms a cage around the solute. This makes sense. The atoms or molecules of the solute must become evenly distributed to dissolve, and that means that they will now be surrounded by water instead of in one clump together. So these little cages have a different energy than when it's all in solid form. Let's talk about the difference between dissolve and dissociate. You will see both words when you work on problems with solution chemistry, so we need to know the difference. Both things that dissolve and dissociate will form homogeneous solutions, meaning they're evenly mixed throughout. They will have the AQ designation in chemical formulas when mixed with water. Now, when you dissolve something, it may or may not break into ions in solution, but when you dissociate, it always breaks into ions. That's the definition of the word dissociate. We'll compare sugar and salt to get a better handle on this. Both sugar and salt dissolve in water, but when I put sugar in water and dissolve it, the sugar makes a homogeneous solution where the sugar molecules are still sugar molecules, just evenly mixed. They're spaced throughout the solution. It dissolves. It does not dissociate. When you put salt in water, sodium chloride, dissociates to form Na plus and Cl minus ions in solution. In other words, it both dissolves and dissociates. Now, the thing that you need to take away from this is that ionic compounds and acids will dissociate. They'll split up into ions. They will sometimes dissolve and sometimes not dissolve well, but either way, if they do dissolve in water or in anything really, ionic compounds and acids will dissociate. Now, covalently bonded compounds that are not acids may dissolve, but they do not dissociate. Sugar is a covalently bonded compound. It dissolves, but it does not dissociate. All right, so keep this straight in your head. Dissolve means that it mixes with water evenly. Dissociate means that when it mixes with water evenly, it breaks into ions. When things dissociate, we sometimes represent them as their ions. For example, if we mix ammonium sulfide with lead 2 nitrate, we make lead 2 sulfide solid and aqueous ammonium nitrate. Ammonium sulfide, lead 2 nitrate, and ammonium nitrate all dissociate into ions, so we can rewrite the equation to show the ions in solution. To keep the equation balanced, we need to take the following into account. 1. If there's a subscript in the chemical formula, that indicates the number of atoms or polyatomic ions we have. So for example, we have a subscript 2 here, and it says that we have 2 ammonium ions. We have a subscript 2 here. It means we have 2 nitrate ions. Okay. So the subscript becomes the coefficient when you write it as an ion. Now, 2, the coefficient in front of something must be applied to all the things following. So here we go. We have 2 times ammonium nitrate, so then we end up with 2 ammonium and 2 nitrates. Now that's kept our balanced chemical equation balanced, and there is an important side note here. If you have both a subscript and a coefficient, you have to multiply them by each other to find the correct number of ions to include. Now, finally, the charge on the polyatomic ions is what we defined it as when we're learning about them, so those you should know, or at least be able to look up. And the charge on transition state metals has to be inferred from the chemical formulas. So I kept saying it was lead 2 nitrate, and I knew that because nitrate has a -1 charge, and there's 2 of them. Therefore, lead has to be +2 in order to balance that negative. Now, you may notice that when you look at this, it's kind of a lot to look at. Ionic equations tend to be very, very long. So we're going to simplify this on the next slide. Brings us to the topic of net ionic equations. A net ionic equation gets rid of anything that is the same chemical species on both sides of the ionic equation. So if you look at our example here, we have ammonium and nitrate ions on both sides of the equation, and so we cross those suckers off. Those are called spectators. They're watching the other chemicals react. Once you have crossed off your spectator ions, rewrite the remaining materials, and that is your net ionic equation. It simplifies things so it's easier to look at, but it can be confusing when you're in lab talking about adding things into solution. You have this net ionic equation for the reaction, but you've added ammonium sulfide into the beaker. So you're looking at the net ionic equation. It has nothing about ammonium, but your instructions say it has ammonium. What? Remember that you get rid of spectator ions when you write the net ionic equation. So if it isn't mentioned, it doesn't react. Okay, it will take a little bit while to get used to that, and it's going to keep coming up in lab again and again and again. Just remember, if you're given this net ionic equation and you look at the ingredients and it's got stuff that isn't mentioned, that's because it's a spectator. It doesn't react. All right, so I want you guys to practice this. I want you to do all of these and write ionic and net ionic equations if you can. All right, so the first two, you can in fact write ionic and net ionic equations. Hopefully you got what I have here. But that last one, sugar doesn't dissociate. The C2H5OH, which is an alcohol, ethanol in fact, doesn't dissociate. This is fermentation of sugar. So it doesn't make an ionic equation. There is no way to do it. It doesn't dissociate. I wanted to make that point drive home. We have stuff that dissociates, that's ionic, or it's an acid, and we have stuff that doesn't dissociate, and that's organic compounds that are covalently bound. All right, moving on. To summarize, a solution is a mixture in which the solute, which is in the minority, is evenly distributed, in other words, a homogeneous mixture, with the solvent, which is in the majority. Things with AQ that dissociate can be written as ions in an ionic equation, and a net ionic equation gets rid of spectator ions from the ionic equation. Finally, ionic compounds and acids will dissociate, but covalently bonded compounds that are not acids may dissolve, but do not dissociate. It's an important distinction. Try to remember it.